Okay, so I did a video about RLC circuits, so a resistor and a capacitor in series. And now we're going to add an inductor. So let me just start off with an inductor. I made this inductor. An inductor is really just a coil of wire. And this one is wrapped around an iron core. That makes it a little bit better, a higher inductance. But this works with Faraday's law. So if you remember Faraday's law, it says that a changing magnetic flux induces a potential difference. So also a electric current makes a magnetic field. So if you consider two parts of this loop, if you consider this part of the loop and this part. So if I have a changing current, that makes a changing magnetic field over here. But that changing magnetic field induces an electric field in the opposite direction of the electric field that made this current. So the result is that if I have a constant current going through this inductor, it doesn't really do anything. It makes a magnetic field, but nothing magic happens. However, if I change the current, that makes a changing magnetic field, which makes a changing flux, which makes a voltage across here that's in the opposite direction. So this resists changes to electric current. Okay, so, and from that, I have the following relationship for the voltage across an inductor. It depends on the rate of change of current. The change in current divided by the change in time. It's really a derivative. And L is the value of the inductance in henries. Okay, so let's just review the other elements that we're going to be looking at. A resistor has a potential difference across it of the current multiplied by the resistance. That's important. And so here you see we have one that depends on the change in current. This one depends on the current. And then finally we have a capacitor, which depends on the voltage across it, depends on the amount of charge. And so these are all related to charge, right? Because here we have the charge, and then the current is the rate of change of charge. And then this is the rate of change of the rate of change. So it's sort of like Q, the rate of change of Q, the rate of change of I. Okay, so it can be a complicated situation, but I'm not going to get into differential equations to solve this. We're going to do it numerically. And to do that, I'll show you how we're going to do it, but we're going to break these into finite, small time steps and assume that Q is constant during those time steps. So we're actually going to build three circuits. The first one's going to be this. Imagine that I have a capacitor with charges on it, and I have it connected to an inductor. So this little squirrely thing is an inductor. Don't get that confused with this, which is a resistor. When I close this switch, then this current is going to flow this way. However, right now there's zero current. So when I close the current, I go from zero current to some current. So I can get a very large change in I. That change in I will produce a potential difference across this that will actually cause the current to flow back the other way. So we'll have charge going off the capacitor, and then because of that rate of change, we'll have charge going back onto the capacitor. And then the whole thing will repeat itself, and this will just oscillate back and forth between those two things. Kind of cool. Okay, now if I go down here and I add resistor into the situation, the same thing happens, but this kind of drains off some of the energy, right? So if this is going that way, and this will dissipate some energy, so eventually we'll lose all the change in potential. And this is like a damped oscillator. And then over here I could have a voltage source that's changing, and this will be an RLC circuit with a voltage source. Okay, so let's start off with this one. And what I'm going to do is use the loop rule, which says that if I go around a loop, a complete loop, and I add up all the changes in potential, then I will get to zero. Okay, so in this case, if I start right here and go across, I have the voltage across the capacitor, voltage across the inductor, and that has to be equal to zero. And we can use that to solve for some stuff. So let's do that. So here is my circuit. Let's draw that again. And let's say it's closed. So this is plus Q minus Q, and that's the inductor. So delta V loop is equal to 0. So it's going to be the voltage across that capacitor, which is going to be equal to Q over C minus L times delta I over delta t equals 0. Okay, so we actually have two things here. We have three things. We have Q, we have I, and then we have the rate of change of the current. So just to make things easier, I'm going to call this, I'm going to define a new variable, and this is not used anywhere. I'm just using it here because it makes sense. Alpha is the rate of change of the current, and I is the rate of change of the charge. Okay, so this is like, you can think of charge as position, I as the velocity, and delta I over delta t as the acceleration. That's why I used alpha. So it's not, but it's a lot like that mathematically. So that means this equation becomes Q over C minus L alpha equals 0. I'm going to solve this for alpha, and I get, if I move that to the other side, I get alpha equals Q over LC. This is my first step. So this is a tough thing, right? Because alpha depends on the rate of change of current, which depends on the rate of change of charge. And here is the charge. Okay. So in order to solve this, what I'm going to do is break this into small time steps. Let's say 0.001 seconds. And during that time, I'm going to assume the charge on the capacitor Q is constant, even though it's not. So I can get a value for the acceleration. The alpha, it's not the acceleration. Okay, so that's the first step I'm going to do. Now if I go up here, I can say 2 alpha equals I2 minus I1 over delta t. So this is the change in I, right? So I2 is the current at the end of the time interval. I1 is the current at the beginning of the time interval. If I solve this for I2, I get I2 equals I1 plus alpha delta t. So this means I just calculated alpha. I know my time interval. I know alpha. If I know my initial condition, what current I start with, in this case, if I have a switch, that would be 0. I can solve for the current at the end of this short time interval, which doesn't get me there, right? But it gets me somewhere. It doesn't get me all the way as far as I want, just for that short time interval. But here I'm assuming alpha is constant, which assumes Q is constant, which is not. But with a small enough time interval, it's kind of true. Now I'm going to do the same thing. I'm going to use the definition of I, Q2 minus Q1 over delta t. If I solve this for Q2, I get Q2 equals Q1 plus I2 delta t. So this just says I, but I just calculated I, and I found the new version. So I'm actually going to use the current at the end of the time interval. That might seem weird. I get that, okay? But that's what I'm going to do. And then finally, I'm going to take this. T2 equals T1 plus delta t. So I'm going to update the time. So this means I'm now, if I do these 4 calculations, I'll have gone through 0.001 seconds of calculations using an approximation. Now, if I want to get to a time of 1 second, I would need to do 1,000 of these loops. But this is a loop. I go back up here and I do it again. Now I calculate, I have I3 and I2, Q3 and Q2, and so forth. And I can just keep doing this. So this is a numerical calculation using the Euler method of solving a problem by looking at the numbers. But of course, you need to start somewhere. I need to know the initial conditions to find this first alpha, and I need to know the first I to find the next I, and I need to know the first Q to find the next Q. So I have to have all those things. So let's just say this is 5 volts across that capacitor, and I can solve for the charge, and then I can see what plays out. Okay, so we're going to do this in Python because I don't want to do 1,000 calculations for just 1 second. But just so you know, people did do that. Okay, before the electronic computers were people that would do these calculations by hand and get the numbers, and it's tedious. And that's why we want a computer to do it. Okay, so let's switch over to the computer, and to get this thing to work, I'm going to use my these initial conditions for my situation. So switch over to computer. Here we are. Okay, so I'm using GlowScript VPython in Trinket. Okay, so Trinket is just an online implementation of this. There is an offline implementation too, but this works just fine. So let's just start off with what I have. I have EMF equals 5. We don't want to put units. These are numerical calculations. That means that we have to use numbers. I can't put units in there because Python's like, I don't understand what you're talking about. If I say 5V, it doesn't get it. It doesn't treat it like a number. I'm going to use a capacitance of 1 times 10 to the negative 4th farads. L is 0.2 and R is 10. T is 0, dt is 0.001. Okay, so another thing is I want to make a graph of the voltage on the capacitor as a function of time. So I'm going to need to make a graph. So let's do that. T graph equals graph. Let's say this LRC circuit is the title. Let's give it a title. Title equals. We need an x-axis. I will include down below a link for my graphing tutorial in Python. So x title equals time in seconds. And then y title, I'll just put it as voltage. Let's call it V in volts. Because it could be the voltage. I could plot anything and I don't have to change it. And let's do this. Let's say width equals 500. Height equals 350, just so it'll appear fine. Now, the other element of making a graph, I need to add in a function to plot. So let's call that F1. Let's just call it F1. It could be any name you want. It's a type of object called G-curve, and I'm going to make it blue. So this is what makes GlowScript VPython so awesome, is that we have these things built into graphs. I can make a graph with just that stuff right there. And just to show you how that would work, if I say f1.plot 1, 1, it will plot the data point 1, 1. It doesn't care what the values are. And then I can plot another point, f1.plot 2, 3, 2, 4. Now let's just save this and run it. More RLC stuff. I'm changing that because I had a previous calculation. I want a new name. New. Okay, so then it plotted those 2 points and connected a line because it's a G-curve. It doesn't actually plot the points, it just connects the line between them. That's how these graphs work. They're so easy to use. Okay, so I don't want to plot those up. Okay, so let's do this. I said I was going to do 1 second time interval. So let's say while t is less than 1. Right, so right now t is at 0. In Python, loops start with a colon. A while loop says do the following after the colon, and anything that's indented is part of the loop. So the first thing I'm going to do is to calculate alpha. Just like I said, so alpha, I'm looking at my sheet, is Q divided by L times C. And I never said what Q was. So let's go up here and say Q equals, let's see, Q is C times EMF. Right? I wanted it to be 5 volts on the capacitor. The voltage across the capacitor is Q over C. So if I take C times EMF, I'll get the charge. I have to have that initial charge. Now, the other thing I need to know is my initial current. So I'm going to say I equals 0. That means the switch starts open. It doesn't have to. It just is in this case. Okay, so I calculate alpha. Next, I'm going to update I. I equals I plus, let's put a space, equals I plus alpha times dt. So this is not a normal equation. This equal sign in Python means make equal to. Okay, those i's don't cancel because it says take alpha times dt, add it to the value of I, and make that the new value of I. So I don't need I1, I2, I3, I4, I5, all the way up to 1,000. I just need one I, and it's going to change. Okay, now I'm going to change the Q. Q equals Q minus I times dt. Is that right? Q is Q minus I times dt. Why? Because Q is the charge, I is delta I over delta t. That's the flow of charge. But Q is the amount of charge on the capacitor. So as the current goes, it decreases the charge on the capacitor, so that I have to subtract that amount each time. Otherwise, I would just be adding the current to the capacitor each time, and that would be weird. Okay. Now I need to update time. So say t equals t plus dt. And finally, I need to plot the stuff. So I'm going to say f1.plot. What x coordinate do I want? I want time. What y coordinate do I want? I want the voltage across the capacitor, which we'll call right here is Q over C. And let's see if this works. I don't know that it will. You never know. Things just might not work. Okay, but it looks like it did. So here I get an oscillation between the two. It's really fast. Let's just go look at this for 0.1 seconds. So I'll say 0.11, whatever. There. And this is exactly what you expect. I actually probably need a smaller time interval. You can see a little jaggedness up there because from here to there is one time step, so it's actually kind of small. If I'm looking at this small of a time interval, I actually want to make that a little bit smaller, and the computer doesn't care, but now it's nice and smooth. So there you go. That's my RLC circuit. It's an oscillator. It just oscillates back and forth. Just so you know, what if I change something? If I make the inductance larger, let's say 6.6, it decreases the frequency, so it takes longer to oscillate. Let's go back and change that to 0.2. What if I make this bigger? Capacitance is 2 times 10 to the negative. It also decreases the frequency and makes it spread out. Okay. So you can see my comments right there. So let's now go back to the paper and add a resistor. What if I want to add a resistor in here? Well, the only thing that's going to change is this first step. I need to calculate the new alpha, but this step and this step and this step will all be the same. Okay, so let's draw a circuit with a capacitor in there. So here's my a resistor. Here's my capacitor. Here's my switch. Here's my inductor. I'm going to make it nice and loopy. And then here's my resistor. So again, I can use the voltage loop rule. I can say delta V loop equals 0. And that's going to be equal to the voltage across the capacitor, Q over C, minus L delta I over delta T. And then I also have the voltage across the resistor, which is going to be minus IR. So again, I'm going to put in alpha equals delta I over delta T, which is just a made-up step just to make things look nicer. And I'm going to put that in up here. I get Q over C, and I'll add that to the other side. Minus IR equals L alpha. I added L alpha to both sides. Now I solve for alpha, and I get alpha equals Q over LC minus IR over L. So, and you'll notice here, if I let R equal to 0, then I get back to the same equation I had before. But this is what I need to add into my thing, this I times R over L. So let's do that. Let's switch back over here to Python. And I'm going to say alpha, looking at my thing, is just going to be minus I times R divided by L. And I have all those values. Oh, I'm going to put this back at 1. And let's see what happens. Check that out. So it's still an oscillation, but it's a damped oscillation. It decreases in amplitude over time. Let's make that run for a little bit longer so we can see the whole thing. Edit. Let's go for 0.2 seconds. There you go. Is that not lovely? And all I had to do was add in that one element of the R. So this is an LRC circuit. And I could easily just change that R to 0 and it'd go back to what it was before. Okay. What if I increase the resistance? What would happen then? I mean, you can think about what you might think would happen. Change this to 50. And now look, it didn't even make a full oscillation. It just damped down right away and stopped. And then I can make it just 5. and it would damp down less. Okay. So we don't have to solve those differential equations. We can modify, we can numerically calculate them this way. Okay, now we have one more circuit to look at, and that is, what if I add in a driving force? So let's set that up. Where'd my pin go? Here's my pin. Okay, so this is the symbol for a changing voltage. It's a battery that has a changing voltage, and we'll write down a equation for that in a second. I don't need a switch really, and I'm going to have a capacitor, an inductor, and a resistor. So let's just say V as a function of t is going to be V0 cosine omega 0 t. So this says that my voltage is going to be some oscillating trig function, and where V0 is equal to 5 volts. And now I need an omega. Let's just pick omega is 0.1. Let's just pick 1. Now, I'll tell you right now, if you went back, let's actually go back real quick to this and run this. What's the frequency of oscillation for this? So if I look at one complete oscillation, it goes from here to there, and that's about let's say 0.28. So t is 0.0287. So I can use that to calculate the frequency. So omega would be, is it 2 pi? It's 2 pi over t, where t is the period. Okay, so let's print that out. Let's print out the frequency. I mean, I have a calculator right here, right? So I don't need to do it. So let's say omega 0, I'm going to call it omega 0, is going to be 2 times pi divided by 2.87 e to the negative 2. That was what I had, right? Yeah. And then let's print that. Print omega 0 equals omega 0 radians per second. And I get 218. Okay, 218.9 radians per second. Okay, that's my omega 0. So we can try an initial omega of, let's just say 200. Okay, and then we'll change that around. So now I need to switch back over here. So what do? Well, now again I use the loop rule, and it's the same as before, except I have this voltage in here. So if I go across this, I get 0 equals V0 cosine omega 0 t plus Q over C. I'm trying to think that should be plus or minus. And then I get minus L delta I over delta T minus IR equals 0. So in this case, I again want to substitute alpha in right here and solve for alpha. So if I move this term to the other side, I get alpha equals V0 cosine omega 0 t, all of that over L, plus Q over LC, minus IR over L. And that's my alpha. So all I need to do is add this term in my numerical calculation, and it should work, right? Because if I take that term away, I get what I had before. And so all of this reduces back. I can reduce back to an RLC circuit by letting this V0 be 0 and R equals 0, and that does give me what I had. Okay, so this should work. So let's go up here, back to Python, computer. And yes, I am going to give you the code because I care. Okay, let's put up here omega 0 equals 200. I just picked something. Okay. And then down here, I'm going to say alpha equals V0 is actually EMF times cosine omega, it's called W0 times t plus. Now that's not dt, right? Because this changes with actual time. All of that divided by L. Okay, I think that should work. Let's just see. Yeah, it did work. Okay, let me run that for a little bit longer. So let's run this for, let's say 8.8 seconds. Okay, so we get this oscillation right there. Let's just change that frequency of this to something smaller, like 100. And you get something different, but you'll notice that the amplitude is smaller too. Let's do 10, something really low. Okay, so in this case, what happens is that's a very, very low frequency, and it's almost like it's just driving it back and forth at that same frequency. So this circuit's going to behave differently for low frequencies than it does for high frequencies. Let's go back over here and put this at, let's say 500. I think that's too high. Yeah. But now you see this voltage is very low. It's around 1 volt. So at, actually, let's do 219, which is what I calculated the natural frequency to be. I get 20 volts. Okay, so it's kind of like this is a resonator circuit. If I get the voltage of the source equal to the resonance frequency of the circuit, then it's like pushing a swing back and forth at that same frequency. So if I go to there, I'm not going to derive it, but this, let me just show you. The resonance frequency omega 0, with the resistance is 0, is 1 over the square root of L times C. So let's print that out and see what I get. Because we measured it experimentally, remember? Let's see. Okay. Let's just print. Print omega 0 equals 1 divided by square root L times C. C. Let's just print that. See what happens. 223. So the resonance frequency with and without the resistance actually are different. Okay. So the resistor does matter. But there you go. There's your LRC circuits. You can actually make some super complicated circuits where it oscillates back and forth at different frequencies, but I'll let you play around with those numbers. I just want to get you to model this, make this voltage graph, and see what happens. And there you go. So we'll stop there.